Okay, so today's experiment, we're going to be doing nuclear radiation, looking at nuclear decay, and how we can shield from it, and what the effects of time, what the effects of distance are on the exposure to it. Nuclear decay, we're talking about nuclear reactions, which will go much more into depth in lecture. But, I'll leave these on right now. But in essence, most chemical reactions involve the electrons only. The nucleus, with the protons and the neutrons, don't participate at all in a normal chemical reaction. In a nuclear reaction, the nucleus is what's happening, and there's nothing with the electrons, actually. And so it's all with the protons and the neutrons. Some isotopes, remember isotopes, atoms, elements with the same number of protons but different number of neutrons, right? Some isotopes are stable, and that's what we usually see in everyday life. Other ones are unstable. They actually decay. Now, they can decay very quickly. They can decay very slowly. That has nothing to do with whether they're stable or not. Okay. There are several ways that they can decay, but we're going to look at the three main ways today. Those being alpha decay, alpha, beta, and gamma. Just the first three letters of the Greek alphabet. Alpha, beta, and gamma decay. What's happened here, very quickly again, is that the nucleus is releasing some type of a ray. They don't use the word ray so much anymore, but because they're actually particles, they're subnuclear particles that they're releasing from the nucleus of the unstable isotope. When that happens, it becomes a stable isotope, or eventually works its way down to a stable isotope. All right, what are those that are being released? Well, an alpha particle is the first one. An alpha particle turns out to be the same thing as a helium nucleus. And if you think about that, a helium nucleus would have 2 protons and 2 neutrons. And so you could write that as an He with a 4 and a 2. 2 protons and 2 nucleus. 2 neutrons. No electrons, right? So it's actually a positive charged thing that's going off. It's a 2 plus. Okay, the second type is the beta decay. Beta turns out to be the same thing as an electron. And so that would be an E with no mass and a -1 charge. Third, gamma, that is pure energy. It doesn't have mass, it doesn't have a charge, and so its symbol would be a gamma with a 0 and 0. It's kind of a pure energy being released, like a photon, right? Like a photon. All right, so the nuclei are releasing these 3 particles of different types. And again, we're going to investigate how fast. And by fast, I mean how many counts per minute. When we put a detector on it, say we have our sample, and it's perhaps releasing some particles, then we put some detector over here, and it's going to eventually pick up and detect that some particle has been released, colliding with our detector. It will make a click sound. It's essentially an electric current to a speaker just detecting the motion of one of these charged particles. It's called ionizing radiation. Don't worry about that right now. So every time you hear a click is when the detector has found or detected one of these particles being released, either an alpha, a beta, or a gamma. And so you'll see with our detector go click, 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 just depending on it. Okay. And so we're going to count how many clicks or how many counts per minute. CPMs, how many counts per minute. So we turn it on, we wait a minute, and we count to see how many we get. And a very hot source would give you a lot of clicks per minute. A colder source, of course, not so many. Also, just coming from our environment, especially from outer space, there's plenty of these particles being released and bombarding all the time. We're constantly exposed to that. We call that the background radiation. And that's going to be the very first thing that we're going to have to measure. Because if there's background radiation causing counts per minute, we need to subtract that off of what's coming from our source as well, because we're going to be measuring both at the same time, obviously. So we're always being exposed to these things. Let's start with the background radiation then.
Click.
Okay, so here's our Geiger counter. It's going to measure the counts per minute, like I said. And this is the actual detector. I will show you. I didn't think about this. Let me slide this out of here. Here's the window that, can you see that okay? here's the window that the particles would enter and then cause a little current to go through, and then you hear that as a beep. I've got this secured up, hanging here in the air, because later on we're going to move it up higher so we can get more distance, and we'll measure that. So right now that's that. Okay, and so first of all, with no source at all present down here, nothing, so all it's going to be receiving is what's coming from the background information, or the background radiation. So here's I'm going to reset it, and we'll set it to go for 1 minute. And you should be taking your data, of course, on your data sheet. This is from table 1. Okay, there we go. Count. And you can see every time it detects a count, the counter goes up here. So we'll wait for it to stop for 1 minute. We'll count. Like we said, there's no source, and it's already been up to 10 counts. So we always have background radiation that we're continually exposed to. I forgot to check to see if when the minute was, but I think we're up. I think that was a minute. Next time I'll make sure to set my watch just to make sure.
Yeah.
All right, so there's our first minute. 32 counts. That was the background radiation that he detected. 32 counts. So we got to repeat this 2 more times, so we'll get an average. So I'm going to reset that, and we'll start again. Okay, there we go. Oh, wow, pretty close. 31 this time, so fairly consistent. And we'll do it one more time. Go. Okay, there we go. There's a minute. 33. So fairly consistent. Very nice to see. Our background radiation. And that was a mixture of alpha, beta, and gamma. Actually, a couple other ones as well. I think in the future ones, if I put my phone here a little bit, would that help to count down? I mean, like if I put it here, can you see that on the camera? Yeah? Yeah, I don't know, that might help just so okay, a minute's up, and we'll start. Okay. Part B, radiation from different sources. And so we have here some sealed sources of radiation. We'll start with this one, I think. This is, let me hold it up nice and close for you. This is a little disc, and you can see it is a beta emitter. And up there it says, oops, I just lost the focus on it. There we go. It says 28.8 years. The 28.8 years is the half-life. In other words, if this source, it's inside, just encased in this plastic here. If this source initially had, say, 100 counts per minute, then 28.8 years later, it would only have 50. And then after another 28.8 years, now it would be down to 25. Every time you go 28.8 years, it gets half, or it gets cut in half as far as its counts. So this is a beta emitter, and we're going to simply measure, in part B it says, at 10 centimeters from the probe, we're going to measure the distance, the identity, and then the counts. And we'll do this twice. So, the first thing is to set it at 10 centimeters. This is where we can move this up and down. I need to go 10 centimeters up. There's just a little bit there, but that's okay. That's definitely more than 10 centimeters. The detector's right at the bottom there, so we're at about 23 centimeters. Let's go down with this. And actually, right about there. Pretty close. Doesn't need to be exact in the ballpark of it. Okay, so here's again the source. Beta emitter. And actually, I didn't show this to you either. At the very top, it says what it was. Up there, it says SR90. So that's strontium-90 is the isotope there. All right, so we're going to just put it right there, right underneath the detector. And we'll count this for 1 minute at a 10 centimeter distance from there. All right, reset and count. Okay, so there we go. There's our 1 minute. 966. Hopefully you can see that on the camera. 966 counts. We'll reset it and do it one more time. Okay. 1 minute there, this time 1009. Okay, so under the table 2 for the item, again, that was strontium-90, SR90. I'll show you that one last time. That was the item, and it's a beta emitter. All right, we've got 2 other sources here that we can test. Next one. There we go. Cobalt 60, half-life of 5.27 years, and it's a gamma emitter. All right, so Cobalt 60. So again, we'll just go ahead and put it right underneath the source like that at 10 centimeters. We'll reset this and we'll count for 1 minute. I'm getting a message. Okay. And so that one, 93. So it's above background. Background was 31-ish or 32-ish. So that's not as, we would say, it's not as hot of a source, but still definitely above background. We'll reset it and we'll try this one more time. Okay, 86. All right, we'll try one last source for table 2. One last source we have here. So this is cesium-137. It emits both beta and gamma. It's got a half-life of 30.2 years. All right. Put that down there. And reset and go. Okay, very hot source, compared to the other ones anyway, 2,530. Reset and do it once more.
one's 2,463. Okay. So that one is the hottest of the samples that we've had. All right, so there you go. That's for part B. We tried 3 different sources. You can see, depending on the source, it has different counts per minute. And again, one of them, the first one was a beta emitter, the second one a gamma emitter, the third one both beta and gamma. We do have, let's just show this to you as an example. We do have an old alpha emitter, so we haven't done that one yet. This is polonium-210, but as you can see on the label, its half-life is only 136 days. 130, so it cuts in half every 136 days. So, I mean, roughly 2.5 times a year it's going to do a half-life. And you can see in the red stamp, this is from 2004. This is 2020, right? So this is 16 years old. It's been going through many half-lives. This one is pretty much totally decayed. This one, the counts are not any higher than the background, and so there's no point in measuring that. So unfortunately, we can't show you an alpha emitter. Okay, so part C, we're going to investigate 3 things. What can we do to shield ourselves from radiation? Number 2, what is the effect of exposure as far as time? Short exposure, long exposure, how does that differ? And 3, the distance. How close are we versus how far away are we? How does that affect the number of counts per minute that we're exposed to? And so we're going to do that for each one of our sources. So we'll go back to the very first one that we did before, the beta. This is the, the strontium-90, which is a beta emitter. And we'll put that down there as before. But this time we're going to try different shielding. The first one, it's just a little cardboard window there with some paper. So it's just paper. How well does paper shield the detector? So we'll slide this in right in front of the detector. Remember, the detector's looking down, and so now we got a piece of paper there. And we'll see, does that shield us from the beta rays that this is emitting? And so we can run this, and we'll compare it to what we got in the last section. All right, so reset. We'll do it for 1 minute, and we'll go. Okay, here's our 1 minute. 898 counts per minute. So I don't know, did the paper shield as much? I'll leave for you to decide that, compare it to the numbers we got before. Now with that same source, instead of paper, let's try a different shielding. Plastic. We just got a little plastic film in here, and so we'll put that down here. We'll slide that in, like so. So now we got plastic between the detector and the source. Reset and go. Okay, 826. Seems like that might be a little lower. The third type of shielding, again, we're going to go plastic, but this is a much thicker plastic. You can see it's got some thickness to it. So we'll say thin plastic and thick plastic. Plastic goes in, reset, and count. Okay. 70. Clearly quite different. Let me point out to you, 70 is still above background though. So it shielded a lot of it, maybe most of it, but not quite all, right? 70. All right, we have one more shielding material to try. And that's this one right here. This is lead. A lead disc about that thick. I would say it's about maybe 2.5 millimeters thick. And put that shielding in. Okay, that shielding in, and reset, go. All right, 55. All right, we'll try the same experiment with the shielding with the next source, which was the Cobalt 60 source. This is the one that was a gamma emitter. So how well do these same shielding materials work against gamma particles? We'll start with, once again, paper. And reset and go. So you should be recording this on the next table. So this would be table 3B. We've gone to the next source. Okay, 66. Let's try our thin plastic shielding. Reset, and go. Okay, 56. Our thick plastic shielding is next. Thick plastic. Go. Okay, 60. And finally our lead. Okay, 49. Okay, so that explored how the different materials shielded against, the first time, beta particles, and the second time, gamma particles. Okay, next, we're moving on to table 4, where we'll explore time dependence. So how many counts per minute you get over longer periods of time. I think for this one, we'll go ahead and use our beta source, which is the strontium 90 beta emitter. I hope, there we go. Okay, so we'll put that down here. And for the first run, they want 1 minute. We'll reset that and let it go for 1 minute. So this is kind of a repeat of what we did before. That's okay. Yep. Okay, 987. Reset. Next, we'll put the time up to 2 minutes, so twice as long. Reset, and this is the 2-minute run. Go. Okay, there you go. 2 minutes is 2010. And lastly, for 5 minutes. 5-minute run, go. Okay, 4,985. 5-minute run. Okay, next, the last part of C, distance. This will be table 5. This we're going to explore what is the CPMs, how many counts per minute at different distances, away from like that. And so we'll measure the distances and we'll count it. I think we'll use our cesium 137 source. That was plenty hot, so we'll get good numbers even at bigger distances this way. Okay. I am changing the numbers a little bit, all right, and so they have 50, at least my copy has I should show you this. For the distances, we're going to go with 5, 10, 20, 40, and 80. So I've changed those numbers up a little bit. I think that'll be a little easier to analyze when you answer the questions. So let's start with the top one, 80, a distance of 80 centimeters. So I want to get from here down to the ground 80. Or the floor, or the tabletop. So that is going to be way up here. I got it just about as high as I can make it, I'm guessing. Let's see here. To the ground, right there is about 78, so let's even go just a little bit higher. Let's see what we got there. A little bit higher still. There we go. So we're at 80 centimeters high now. So I'll be a long distance away from our source. Right, so I'll just put it right about below it, I'm thinking. Kind of aim it like that. All right, so for 80 centimeters away, and we'll do it for 1 minute. Reset it and count. Okay, 35 pounds per minute. Next, we're going to drop down to 40, so we're going to cut that distance in half. Down, let's see, a little lower. Just a little lower than that. See how close did I get? That's pretty close. 40. We're still right on top of it. Yep. All right, reset that, and at 40, go. There it is, 109. we're gonna cut it in half again now, so that's 40. Now we're gonna go to 20 centimeters away. About there. A little bit of low, oh, just a little bit there. Oh, that's too much. This does not slide very easily, I'm afraid. As they get, that's pretty good. All right, 20 centimeters away from the source now. Reset for 1 minute. Go. Okay, 537. All right, let's cut it in half again. So we're going to go down to 10 centimeters. That should be right about up a little bit. This is so hard to move. There we go. It's stuck on the. That's probably close. Let's about 11. Let's go down a little more. Yeah, there we go. Okay, 10 centimeters away now, here to here. Go. All right, 2,399. And our final distance, 5 centimeters away, which, according to the ruler, 5 centimeters away is this bottom slot. So we will just use this holder here and put it in the bottom slot here. Because I think that's 5. That's more like 6. Let me see. Yeah, that's closer to 5. All right, so 5 centimeters away, just a little bit of distance, reset, and go. 10,291. Distance makes a huge difference in the exposure, and if nothing else, you'll need to crank the data and do the plot and such, and you'll see that. But if nothing else, hopefully you see, if you want to limit your exposure to a radioactive source, even more than shielding, the most important thing is step away. Put some distance between you and the source. Okay, we're done.